sure I have on the screen on the projector. Hello, I'm going to talk about CTX, which is one of my passion or research projects, which is mainly concerned with vector graphics. My name is Øyvind Kolås. I am affiliated with the GIMP project, do many things with raster graphics. I've also done a little bit with vector graphics in conjunction with Cairo in the past. But this talk is going to be about CTX, which is a newish vector rendering library. And we're going to see these demos a couple more times. I'm just going to skip through them. Is a native vector graphics rendering library. What I mean by native vector graphics is that you do the rasterization as late as possible. Ideally, even actually on the GPU. I'm not doing it on the GPU, but I'm not rasterizing to intermediate textures in what I'm doing. It is already used by Cardio, which is a badge from the Chaos Communication Camp, a terminal, which I'm developing for this library, as well as being used internally by GIMP through Gaggle. It has support for floating point storage of colors, not only 8-bit. It does grayscale and CMYK. It can be compiled to be as small as about 70 to 80 kilobytes and use only 20 to 30 kilobytes of RAM and still be able to render vector graphics. The terminal I'm going to talk about is implemented using this vector graphics library. And it follows the same lineage as terminal emulators you're used to. They are emulating the successors of the Digital Equipment Corporation's VT100 from 1978, which was the first terminal that fully implemented the escape sequences that we are used to. It has tabs and multi-document interface, mouse keyboard. It supports some existing raster graphics and kind of strange from the DEC days Sixel graphics. The core of this vector library is a protocol or API, which is a superset of the SVG path data. So here I've written in 4 different ways a subset of a line 2 command in the graphics. So the first one is how it is in SVG path data. The second one is the slightly expanded version that this CTX library also supports. Then it's the C API to route that call. And then it's the internal representation, which for line 2 is 9 bytes. It's 1 byte for the command and 2 32-bit floats. And all the commands in CTX get stored as multiples of 9 bytes. So the curve2 command, here I made a mistake, this should have been a C, a capital C, and is stored as the first curve2 and then 2 continuation commands. The library has polylines, curves, fill and stroke, transform, scale, translate. It has the full PDF 1.2 imaging model. And it also has something that we normally don't have in low-level vector graphics library. It has event handling. So this is a demo that I was using when I was also testing multitouch. I'm rotating the scene, but the event handling that I'm doing works because events get delivered with the transformed coordinates. So you can, as you're drawing the vector scene, you can register callbacks with the current transform you're using at that point. So anything you can draw with the vector API, you can also add interaction to without having to double up and rethink all your transforms and apply them so that they work, or work without any transforms, which is how the HTML5 Canvas API is. You get events in the global coordinates. It also has support for keyboard events. as you might be guessing, this presentation itself is written as a program running with CTX. It has multiple backends, but if you create the CTX context by passing, say that I don't care how wide it is, I don't care how high it is, and I don't care which backend you use, it will, if you have set things up correctly for a microcontroller or for other purposes, try to choose the best possible interactive backend. And the backend, there's many backends. The core of the backend is the function pointer call I'm moving my mouse over now, the process call. And that is processing one of these commands that is in the protocol. And that takes a CTX command entry. And the command is broken down as a union containing line 2, ways of setting the RGBA color, CYK color, curve 2, so I can access them. But this union also has the CTX entry, which is broken down as the 9-byte long segments that the protocol consists of, which is first the character code of the command. So one of the more interesting backends in CTX is the CTX backend. And the CTX backend is a backend for running a CTX program in the CTX terminal. And I think it's time that I stop running this presentation like this and open up a window and launch CTX, which is a terminal. So here we have a terminal. And we can run the same executable, which I was running for the presentation. Now it's going kind of on autoplay. But this is so event handling gets screwed up from time to time. Okay. I will show another example that is not written in C, but a shell script. Let's see, I will do this in this terminal instead. First. I think we get some slightly better colors. So the terminal, the CTX terminal supports the normal escape sequences. So this shell script will first turn on the alternative screen, turn off the text cursor, clear the terminal, and then we have a shell function, which first has this strange X for exit, and then it kind of turns off the alt screen and text cursor back on. But the main core part of this shell script is this command entering a special escape sequence, 200H, and then it starts using this syntax of the protocol. It doesn't use the short version of the commands for start frame and for doing arcs, strokes. It uses the fully spelled out ones. The protocol can both be compact and more verbose, which is easier for writing it. And the protocol, in addition to supporting just the dimensions without units, it also supports specifying units as percentages of the width of the terminal viewport, as well as specifying dimensions and coordinates in relation to the character cells of the terminal. So if I run that script in the CTX terminal, we get this. So that is a shell script which is only spitting out text, and instead of it getting interpreted as colors or bold, it draws an actual vector image. And when you're drawing graphics, you can also embed SVG path data. You could create something in Inkscape or similar, get the SVG path, and then just copy paste it into the code and call CTX parse this bit of path data, and you would get a shape. So you don't have to write down all the lines. And you could also use the rest of the protocol in that manner. And this is what the terminal itself is using to be able to render the vector graphics. The rasterizer, which is what turns the polylines and Bezier curves into a shape that is to then be filled with a gradient, solid color, or a texture, is what is called an active edge table rasterizer. It goes through the shape from top to bottom and figures out which of the lines it consists of are crossing that edge, and it's only working on that. The way it manages to be quite fast is that it has 3 or actually maybe 4 separate ways of doing this computation of each scan line. For some shapes, it is very easy to get completely correct horizontal anti-aliasing, and the common trick for vertical anti-aliasing then is just to do many, many scan lines and average them. So for instance, Cairo does this, and I think it does 15 rasterizations per scan line and averages them, but it gets correct results horizontally anyways. And the CTX rasterizer does that as the fallback in case it's a very difficult scan line. But if all of the edges are more vertical than horizontal and none of them are crossing each other in the scan line, then the cheapest horizontal result with just one computation is accurate. And the middle one I have on this slide, being accurate for gradient spans, is if you don't have any edges that are part of the scan line that are crossing each other, so it just forms gradients from one coverage of alpha to another, and you can piece it together just as one long string of just a complicated gradient. That is the medium expensive version. And the way that CTX manages to cover many, many pixel encodings or pixel formats as well as color spaces is that it doesn't actually do SIMD intrinsics or assembly code. It relies on the auto-vectorization of GCC or CLang. And it manages to get a quite good result out of that. And quite importantly, the compositing is integrated with the rasterization itself, so there isn't even a function called overhead per span or scan line for switching between rasterization and compositing. Another interesting backend, which is normally hidden if you're using CTX, is the hash cache. CTX subdivides the frame buffer or screen in a 6x5 grid. This is to be able to fit total count in a 32-bit integer. And it computes a hash of all the drawing commands which intersects each grid, in each cell of this grid. And this way, CTX can detect whether or which parts of the scene has changed from frame to frame. And if there is no changes, it can just avoid recomputing that part. This is also part of the native vector graphics thinking and rasterizing as late as possible. If the clients are rasterizing into textures, then this optimization of saying that I don't have to recompute this is not possible to do for ZTX. There's also two font backends. The backend I'm using now is the SDL2 backend, which is very rich when it comes to mouse input, keyboard input, other forms of user input. And it serves as my kind of reference of how things should work in the other backends. It also makes it work, I guess, on Mac OS, on Linux, under Wayland, under X, possibly under Windows, I'm not sure. But it also uses OpenGL, and ZTX at the moment is a software rasterizer, so there is a quite large overhead of going through OpenGL to be able to show just a window when I actually just have the raw frame buffer I want to be shown. So I should make a Wayland backend for ZTX so that both the overhead of involving OpenGL goes down, as well as the mostly the overhead is both memory overhead and CPU overhead. And for instance, on a Raspberry Pi under Wayland, it would be much better to just say, here is the texture of the result, do your compositing. There is also KMS or DRM backend, including a FBDev backend. So it is possible to run the CTX terminal or other CTX applications directly on the frame buffer. Here's a screenshot where the most interesting thing is the PID number of the terminal. So I'm not rebooting my computer and trying to get HDMI working to show that this actually works. But it can run with multiple tabs or windows as the standalone graphical environment. In theory, I could do what Apple used to do and save screenshots as PDF with actual vectors inside themselves. And you might have noticed that I actually used CTX the binary to show that image. CTX could be paired running as the graphical environment with BusyBox and then form a full graphical Unix system. And CTX itself is a BusyBox binary. It contains multiple handlers for different file formats. So CTX itself can display an animated GIF, or I can open up a terminal. It is more apparent what's going on if I open up a couple of tabs and move them around and do the same thing. And then we had the image I was showing of some glitches in the change detection, it seems, but I can run it on an I crashed. I will run it outside the terminal then. There are some of my test binaries and programs that work well if they run standalone using, say, the SDL2 backend. Like this, it's playing an MP1 movie. And most of them also works inside the terminal. Another backend which I'm using is the callback-based backend, which is what I'm using on microcontrollers. And this backend isn't tied to a specific display board or display system. It could be used with e-ink or SPI displays. Let me see if I can manage to show some microcontroller-based demos. So first, I want to show the cardio, which is where the experiments with CTX started, which is the badge from last Chaos Camp. And it has been updated since the original firmware, and is actually now doing anti-aliased text using CTX. And let's see. And it has, I want to run Marble. Let's see. Micro Marble. So even the Micro Marble MicroPython games anti-alias graphics, even though it was originally written with the aliased API. And we have another microcontroller here. This one I haven't updated. It's running an experiment where I was experimenting with lower resolution rendering of some things. So the CTX logo in the middle is lower resolution than the display. Lately, what I've been playing with is Raspberry Pi Picos. So let's see here, we have the start of the presentation. And the presentation continues. And here you can see that this test goes slower and slower the more circles we add to get filled. And after 120 frames, it will switch to one that does squares instead of circles. And you will see that squares are quite a bit faster than circles for it to draw. And it's even slightly faster to draw opaque squares than half-transparent squares. So all of those microcontroller demos, we're using the callback backend. And you also can do things like do a preview render in 16 levels grayscale and then re-render in color, or do reduce to palletized 256 colors and then do a re-render in true color. So amongst these microcontrollers, the first one, even though it's slower than the others, has lots more memory and has hardware floating point, which also the ESP32 has. The Raspberry Pi Pico, the RP30 or 40, doesn't have hardware floating point. So when I first had CTX running on it, it was much slower than I hoped it would be. And I have optimized quite a few things to be fixed point. The public API is still floating point, and I think that's fine, but there's still more of the internals in the data processing that I should change over to be fixed point. Then we have another fun little backend. Let's go to our presentations again. And say that we want the backend to be the terminal backend. So this is GNOME terminal showing the same demo. Let's just skip through it a little bit. We're already used to these things. This one is quite fun though, in the terminal using Unicode to fake the resolution. But I want to skip through here a bit, because this is quite fun, because a terminal can also do mouse input. So, and this is where it breaks down. I request a small enough font that this backend says, oh, I can just shove that text straight through. I don't need to fake the graphics. But it gets confused because I draw too much text and I don't abide by the positions I should be abiding by. I could do this, and now I'm actually running kind of like screen. But now, inside this terminal, my clock demo should work. The terminal also has support for pushing audio along with the text over the same link. So that's how the MPEG-1 backend can actually work with graphics. No, with audio and full video. And I have another fun demo that I made work. Let's see, do I? Yeah, I need to enable my document cam again. That I made work just last week. I need to hook up a few things here. Let's see. Okay. We have the logo. We need more light here. So what you see here is top. Or we could run htop instead. And if I So what I essentially have working is the terminal itself running on the microcontrollers, but I cannot run the vector demos in the terminal because I have just compiled the terminal directly and it worked. And it's like, okay. And then I tried to run the other things and I tend to run out of memory. I have disabled the scroll back in the terminal, so there's only like a couple of screenfuls of scroll back. But I do think I will be able to have at least simple vector things working also on the microcontroller version of the terminal. And that is fun. And the other fun thing with the Raspberry Pi Pico, as well as the microcontroller in the Cardio, is that they are dual-core microcontrollers. So there is basically a full Pentium-level computer, which is dual-core. And all of my experiments here are just using a single core. So when there is enough RAM to do something else, either MicroPython or a much smaller interpreter could run on the first or second core, depending on how you rig it up. So I could use a microcontroller as, at least in text mode, a basic single board computer. I can show a couple of more. Okay, neither in the terminal there. Confusing myself a bit here. Another fun example of the shell scripting versions, to draw this thing that comes in line and is part of the scrollback of the terminal, this document is sufficient. It becomes a bit small, but so the way the vector graphics is done integrates with both scrollback and how terminals work. So you could do fancy tab completion or graphics on top of the terminal with lines explaining things, whilst keeping the core interface just using text. And I think I probably should open up for questions. I'll just check my presentation that I had intended to do anything more, or say anything specific more. Yeah, there is a PDF backend as well, but that is preliminary. It supports CMYK. What it doesn't support, which is a little bit too complicated in PDF, is gradients. They are surprisingly complicated in PDF, and that's the reason I haven't done more than just verify that my assumptions of how it should works. And given enough time, I'm quite sure that I will make that part work better as well. But this is fun, and it all has also led me into working on my own languages that I want to try to have on the second core on the microcontroller, but that's probably a topic for another talk. Don't people have any questions for me and the audience?
How long have you been working on this?
How long is it since last camp?
2019.
Okay, so I've been working on it for 2.5 years. I started working on it quite shortly after camp. The cardio bench was what inspired me because it has a very nice 160 by 80 display, and on the rocket I was also playing with doing vector graphics on it, which is an earlier camp badge. And when I got this one, it's like, okay, I've been dreaming of having vectors in the terminal, and I can do vector graphics here as well. And I kind of need a vector rendering system that does CMYK and floating point in GIMP. So my interests and desires coincided and conspired against me, so I kind of had to do it.
There's a question up side there.
Yeah, I have plenty of questions, but I think I can start with one. So my background, I've been doing development of OpenGL drivers before, so I'm not familiar with the first question is actually, this is a pure 2D graphics library, right?
Well, for the transforms, it does scaling, translating, rotation, and perspective. Mm-hmm. So, no. Okay. You can transform both textures and paths in 3D. Mm-hmm. But it is kind of primarily, it's a 2D rendering library in some sense.
It projects 3D into 2D, or do I misunderstand that?
The transformation matrix between user space and device space can be a 4x4 matrix. Mm-hmm. But you're still then doing a 2D space that gets transformed, but it can be transformed in perspective in screen space.
So one of the things I was wondering about, you suggested using it as the backend for instance, a desktop background, desktop in full. So do you do any kind of culling? Or?
Well, it does the change detection I mentioned in that it computes hashes for a grid, so it knows which tiles it doesn't have to recompute. I do not do culling at the moment, saying that I know that it's completely fully overdrawn, so I don't even have to draw the things behind, but those are things that could be added. The text that you've seen, both in the terminal, wherever the terminal was, it doesn't cache the rasterization of the glyphs in the text, each individual letter. So it is actually, as I said, is native vector graphics. It is pushing the Beziers all the way to the rasterizer, and each time you see a character, it gets rasterized. This is beneficial if you actually do kerning and you have subpixel positioning, because you don't want them to be all the same. You end up in a problem where you need to have 4, 8, or 16 caches of each glyph in the slightly small positionings of it to avoid jittering when you're doing like fine typography. So being native vector graphics is an advantage there as well. The way this renderer is structured, you could hook it up to some of the more modern attempts at rendering vector graphics on the GPU. The architecture is not incompatible with that. And that would be, in my opinion, even better than even more native vectors than what I have here.
Lucas, that leads me to another question as well. So you're basically you're drawing Beziers directly in software.
Yes.
I've never tried that. How does that work performance-wise? I mean, on your microcontrollers and everything.
It is satisfactory when you do some forms of change detection or some forms of culling. When I do rendering on my computer, which has a 4K display, being able to very easily multi-thread it is also an advantage. And it is stupidly easy to multi-thread because I have one shared draw list that is unchanged, so each of the threads can just use it. And I use the change detection to figure out which tiles should be queued up for rendering on all the threads. But multi-threading is quite core to be able to do this in a high resolution in software. It would be better to actually use GPU compute to do this.
So I don't see any. So my last question, which is just a small technical one, is there double buffering?
It probably depends on the backend, but yes. The SDL2 backend is kind of, by its nature and how it works, it's OpenGL, and you're updating textures and you're withdrawing, so OpenGL gets double buffering there. On the microcontroller I was running a terminal on barely has enough RAM to have a copy of the frame buffer. So there is no double buffering. It is redrawing section by section of the screen and pushing that over the SPI buses, which is another serial bus where the raw pixels get updated for a region of the display. And this is the same way that e-ink displays work, and that you can do sub-region updates on e-ink. The type of animations and interactions that CTX lends itself naturally to on a microcontroller is the same things you would want to use e-ink for, not heavy animations. So if you treat the high-resolution SPI displays for the microcontroller kind of as color e-ink, then it will work very well with CTX. But if you want loads of animations on all parts of the screen at the same time, it doesn't work well. It works well for the terminal and for a text editor where you move the cursor and doing small edits, because then only a small part of the screen is changing.
So sorry, but the clock you were running, that was not double button, or was it?
I'm not quite sure how to actually reply to that because this is double buffered as well. So would this clock be. I think we're...
Yes, we're out of time. Yes. I'm sure you have a lot of things to talk about. Thank you very much for an interesting presentation. Yes.
Thank you.